Hi guys, my name is Liu. Today I'm going to talk about stochastic optimization for tree-structured stochastic network design. Stochastic network design problem is a general framework for optimization network connectivity. It is defined by a directed graph where each edge is either present or absent with some probability. Management actions can be taken to change the probabilities of each presence. The goal is to determine which actions to take, subject to budget, to optimize some outcome of the stochastic network over a time period. This problem has several applications, including spatial conservation planning, pre-disaster network preparation, and river network optimization. In previous work, a common assumption is that the network parameters, the probability of each presence, are precisely known. This is unrealistic in real-world settings. To solve the problem, we address robust tree-structured river network design problem, where the goal is to decide which in-stream barrier to remove or repair to help fish move upstream and get access to their historical habitats. In this domain, the fish passage probabilities of barrier can only be inaccurately estimated, and the new passage probability of a repaired barrier is even harder to estimate. So in our model, only interval bounds are specified for different probabilities. Figure 1 shows how to encode a river network as a directed rooted tree. Before we start talking about our solution, first we should know how to measure robustness of policy. Assume that given a policy, nature chooses an adversarial policy that selects parameters with their interval bounds to either minimize the ratio between the values of the given policy and the adversarial policy. This ratio called robust ratio, or nature selects parameters to maximize the value difference between them, and this is called regret. In our algorithm, we use these two metrics to measure robustness of policy. Now let's talk about the algorithm. Our algorithm is based on a constraint generation procedure that interleaves between two optimization steps. First, initialize a set C with an arbitrary policy and probabilities. Initialize a counter T and set T to 1. Then step 2, which we call decision optimization. The decision marker finds the best decision policy that maximizes the robust ratio, which can only pick policy parameter pairs from the finite set C, and get the value U, which is the upper bound on the maximized robust ratio. Step 3. Adversary optimization. The adversary selects a new policy parameter pair to minimize the robust ratio with respect to the current decision policy, and get the value L, which is a lower bound on the maximized robust ratio. And last step, step 4. If U minus L no bigger than the threshold, return the decision policy. Otherwise, add this adversarial policy parameter pair to set C and increase T, and go back to step 2. Please note, in step 2, we can use a mixed integer linear programming to solve the decision optimization problem. But the adversary optimization problem in step 3 is much harder. The basic idea which we use is originally used for the barrier remove problem, but we develop an algorithm called rounded dynamic algorithm to solve the more complex part. We first propose a dynamic programming for the problem, which takes exponential time, of course. Then develop a rounding strategy to reduce the rounding time, so it can be fully polynomial time approximation schema. Results. We use data from the CAPS project to test our algorithm and compare it against two baseline methods, midpoint and worst. A midpoint policy is obtained by solving barrier remove problem and assuming true passage probabilities being the midpoint values of the intervals. Our worst policy is basically the same, but we are assuming the true passage probabilities being the lower bounds of the intervals. The policy calculated by our algorithm, we call it MRR policy. First, we evaluate the approximation rate of the RDP algorithm in real problem. The results are shown in Figure 4. Where mu and constant are different rounding parameter. The DP algorithm runs out of memory on networks of larger size. From the figure, we can see that the RDP algorithm produces nearly optimal policy parameter pairs. Then we test on a larger network to see what the value of rounding parameter, say k, is sufficiently large for RDP algorithm to produce good robust ratios. The optimal objective value is not available on this network. The results are shown in Figure 5. We see that robust ratio converge within 2 minutes for all testing policies, and random policies are much worse than two baseline policies. The value of k in the convergence area implies that it is sufficient to produce nearly optimal solutions. On the same network, we compare the robustness of the three policies using the value of k in the convergence area. Figure 6 shows how the robust ratio and regret computed by MMR changes as the size of interval varies, the beta, and we can see MRR gives the largest robust ratio and the smallest regret. In another larger network, we obtain results similar to those shown in Figure 6. We visualize the computed policies in Figure 7. We can see the MRR policy is more robust by allocating the budget to several important areas so that the adversarial policy cannot achieve much better value. Conclusion. We describe an approximate robust optimization algorithm for a tree-structured stochastic network design problem, which is motivated by the river network design problem for fish conservation. Empirically, we show that the policy computed by maximizing the robust ratio are more robust than policy computed by two other baseline methods. Besides finding policy for high robust ratio, our algorithm can also provide policies with small regret on large-scale networks. This algorithm provides new computational tools for environmental scientists who tackle decision problems with imprecise models.